So in this video, we're going to be looking at reactions of transition metals as well as qualitative analysis. Now, when it comes to our reactions, we need to know three when it comes to transition metals. The first one and the most important one is going to be ligand substitution reactions. The next one is precipitation, which you've already seen in module 3, and then redox, which you've seen in module 3, 5, pretty much everywhere, to be honest. Now, starting off with ligand substitution reactions, we need to be aware that, of course, in this reaction, we end up with one ligand replacing another on a transition metal ion because it binds more strongly, right? It's in its name. We've got ligand substitution. We're swapping one ligand out for another, but in this case it's going to be one that binds more strongly. If we were to look at the order in terms of the three ligands we need to be aware of and their relative strengths of binding, we know that ammonia is going to be, of course, binding the most strongly, followed by, of course, chloride ligands, and then water ligands itself. That's going to be the weakest. Now, if we were to look at these three reactions you can see over here, we've actually got three examples of equations that you need to memorize. You've got different color changes for all of them. The first one goes from pale blue to yellow. The second one is going to go from pale blue to deep blue, and then the last one is going to go from violet to purple itself as well. If you were to look at the equations for all of these, you can see here with the first one, we've got 4 big and bulky chloride ligands that are going to be swapping places with 6 slots of water ligands. We end up with ligand substitution taking place, but our shape is actually changing, going from octahedral to a tetrahedral complex. It's not going to be square planar because remember, we've got 4 chloride, 4 bromide and 4 iodide ligands. They would, of course, result in a tetrahedral shape because they're quite big and bulky and they can't actually lie flat as a molecule. You can see we've released 6 slots of water. The charge of the actual complex has changed from a 2+ charge to a 2- charge, and that's because of the negative charge on the chloride ions itself. If you were to look at the next one, right, we end up with 4 lots of substitution taking place. 4 lots of ammonia swaps places with 4 out of 6 of the water ligands, and you end up with this massive complex over here, and this can actually exhibit cis and trans isomerism. Because the coordination number is still going to be 6 in this one, you're still going to end up with an octahedral shape, and you can see we've got 4 lots of water ligands released here. If you look at the last one, we're actually swapping over 6 lots of ammonia ligands for 6 lots of water ligands, and so we end up with, of course, this product over here, which has the same charge in terms of the complex as it did here, because ammonia and water, they're going to be uncharged, but then we release 6 lots of water ligands here as well. Now, in terms of the conditions for these reactions to happen, the first one needs concentrated hydrochloric acid, that's aqueous, and the next two, they're going to need excess ammonia solution here as well. So yeah, moving on then, if we were to look at ligand substitution in the blood, we know, of course, blood, it contains a protein, a quaternary protein known as hemoglobin, and within hemoglobin, the important chemistry part is that it contains the transition metal ion that's going to be iron 2+ itself. Now, iron 2+, right, that's very important because we can actually form dative covalent bonds to it, and a good example is, of course, oxygen. Oxygen, of course, contains lone pairs of electrons that it can donate to the iron 2+. It can actually bind reversibly to the iron 2+, and hence that's going to be carried around the body. Now, once the oxygen reaches where it needs to be, of course, this oxygen is going to be released into the cell for respiration, and of course is going to be replaced by something like carbon dioxide or even water as well. Now, this process actually happens by a reaction that we now know as ligand substitution. Now, so far in module 4, we already know that carbon monoxide is going to be toxic, but we need to be able to explain why it's going to be toxic to humans. Well, carbon monoxide poisoning actually happens when you breathe in carbon monoxide, and that carbon monoxide binds to the iron 2+ transition metal ion, but this time it's going to bind more strongly and irreversibly compared to oxygen, which binds quite weakly and then reversibly, so it can come off and go on where it needs to. Now, if we look at this, right, if we don't actually end up with oxygen going to our cells, but instead we end up with that hemoglobin, right, having a kind of block on it where we can't actually bind any more oxygen on it, that red blood cell actually becomes useless if that happens to all of the hemoglobin on there. So what happens is of course, oxygen can no longer bind on because that's blocked now by the carbon monoxide, our cells end up being starved of oxygen, and so we end up with our cell dying itself. So yeah, if you were to move on, then that's our first reaction done with an example as well. The next one is pretty straightforward. The next one is going to be precipitation reactions. Now this happens where we take two aqueous solutions, we react them together, and we end up forming a solid precipitate out of them. Now in module 3 we actually came across quite a few different precipitation reactions where we were testing for halide ions and so on, but in module 5 you need to learn, of course, the other precipitation reactions that happens with our transition metals. Now normally this happens when we add, of course, dilute ammonia solution, or when we add dilute sodium hydroxide solution, and it's going to be dropwise to start off with. Now sodium hydroxide, which is just going to be NaOH, you know that that's going to, of course, dissociate, and you end up with sodium plus ions and then hydroxide ions. Now these hydroxide ions, they're going to react with our, of course, transition metal, and we end up forming a transition metal precipitate which has a unique color. Now in all of these we're going to end up with a colored precipitate, and we need to be aware of the equation that's involved to form that. If you were to look at the actual charge of the ion, one pattern is the charge of the ion is going to equal the number of hydroxides you actually add on there to end up forming your precipitate. So copper 2 plus needs 2 hydroxides. If you were to look at, let's say, iron 3 plus as another example, that's got a charge of 3 plus, it's going to need 3 hydroxides to form iron 3 hydroxide itself. Yeah, so just a trend to kind of help you memorize the actual equations that you need to know itself as well. Now we actually end up with the same reaction if we were to add dilute ammonia solution, because we know ammonia reacts with water, and what we end up forming is of course a hydroxide ion, because ammonia is a weak base, it accepts a proton from water, and you also end up forming ammonium ions itself as well. And we're actually interested in the hydroxide that's formed over here, and so we can actually show the same equations when we add dilute ammonia solution as well. Now if you were to look at all of these, right, the first one we end up with a pale blue solution, and that forms a pale blue precipitate for copper. For iron 2 plus it goes from green to green precipitate. For iron 3 plus it goes from yellow to orange brown precipitate. For manganese 2 plus it goes from pale pink to a light brown precipitate, and then chromium 3 plus goes from violet to a green precipitate itself. Now in all of these cases, apart from 2 of them, if we were to add excess sodium hydroxide or excess ammonia solution, we would end up with no further change, apart from the first one, of course, where if we were to add excess ammonia solution, right, not excess sodium hydroxide but excess ammonia solution, we would actually end up with that blue precipitate redissolving, and we end up forming a deep blue solution, and of course a compound that looks like this. Just remember that reaction is a ligand substitution reaction. The same thing happens with chromium 3 plus. If I were to add excess ammonia solution, I end up to get a purple solution, that grey-green precipitate. It ends up redissolving to give me a purple solution, and so we know, of course, we end up with this complex in our ligand substitution reaction. Now another example that you need to be aware of is, of course, if we were to add excess sodium hydroxide, that grey-green precipitate over here, that is going to redissolve, and it actually gives us a green solution, which is going to be this compound over here. Now when it comes to writing an equation, I would always go with what you started off with, and of course what you're going to make. So in this case, right over here, I would go with starting with chromium 3 plus and then having 6 lots of ammonia ligands and so on to actually make this complex itself, right? But we'll look at this in a task later on. So moving on then, if we were to look at our third type of reaction, we need to be aware of course, redox reactions, which we've already come across before. We're just recapping it now. We've got iron 2 plus, right, going to iron 3 plus, and then manganate going to manganese 2 plus. We already know these 2 examples because that comes from our manganate redox titrations, right? We need to remember these 2 transformations, and we need to be able to write balanced half equations and a balanced overall equation for it as well. In terms of course, iron 2 plus being formed from iron 3 plus, right, we know to go in the opposite direction, we would need to use a separate reaction, a separate type of titration, where we're dealing with a thiosulfate redox titration. Now in terms of all of these transformations, apart from the first 2 and of course the last 2, you don't actually need to memorize these in module 5, but you just need to know the appearance of the ions itself and then apply it to the question. The last 2, you've got copper 2 plus forming copper 1 plus, goes from blue to colorless, and then iodide forming iodine colorless to brown. Just be aware, of course, you'll come across this when you deal with other kind of thiosulfate redox titrations as well, where you take the iodine, which is going to be brown in solution, and then of course you add starch, goes blue black, and then your end point, when you react that resulting liberated iodine with thiosulfate solution, you end up with a color change that goes from blue black to colorless itself. If you look at the last one, you've got copper plus forming copper solid, and then copper 2 plus as well. This is a specific type of redox reaction that you need to remember. It is going to be a disproportionation reaction where the simultaneous oxidation and reduction of the same element is going to occur. So that's going to be with copper plus ions itself, where one of them becomes copper solid, it becomes reduced, and another ion of copper plus becomes copper 2 plus, where it's going to be oxidized itself. There's the colors that we need to remember based on everything that we've done in module 5 so far. So yeah, I've got a task for you to try. Feel free to pause the video, have a go, and then resume once you're ready to go over the answer. So yeah, in this case, we're told the flowchart shows the reactions of the complex ion of copper hexaqua ions. That's going to be 2 plus. In the boxes, we need to write down the formula of the species responsible for the observations. So yeah, looking at the first one, we can see we're adding concentrated hydrochloric acid over here. We end up with a yellow solution. What could that possibly be? Well, of course, we end up with a ligand substitution reaction where the shape is going to change. We end up with a tetrahedral complex, and the actual charge of the overall complex is going to change as well. Now the shape changes because of course the coordination number becomes 4. Chloride is going to be big and bulky. We end up with a tetrahedral complex. Now the reaction itself is going to be a ligand substitution reaction, which kind of answers part B itself. So we know of course reaction 1 is going to be a ligand, and then it's going to be substitution reaction because of course we already know that the chloride ligand is going to bind more strongly to our transition metals compared to water itself. So that's going to be ligand substitution for reaction 1 itself. There's 2 marks there so far. If I were to look at the next one, right, I'm going to go right this time. I end up with ammonia, right? And ammonia, we've got it aqueous. But if I were to look at the next step, we're adding ammonia aqueous in excess. So of course we know that in this case, if I just add ammonia, I'm going to assume that that's going to be dropwise. So we've got a precipitation reaction to start off with. So we end up with our copper 2 plus ions, and that's going to be of course aqueous, reacting with 2 lots of hydroxide ions, which we know of course is going to be aqueous as well. And what we end up forming is copper hydroxide, which we know is going to be a solid. So in that case, we end up with a blue precipitate, a pale blue precipitate, where it's going to be of course copper hydroxide. Another mark there. Now of course, if we were to name that reaction, it's not asked us to, it would be precipitation. But the next one, where we add excess ammonia, it's going to be ligand substitution. So again, we'd go from copper 2 plus, and then we'd end up with 4 lots of ammonia replacing 4 out of 6 of our water ligands. So what would I actually end up with in this case then? Well, I would end up with copper, square brackets as well. We end up with 4 lots of ammonia ligands, 2 lots of water ligands, square brackets, and then of course the charge is still going to be 2 plus, because water and ammonia, they're both going to be neutral, aren't they? And there's the next mark there, another ligand substitution reaction. What about reaction 2? Well, reaction 2 is going to be a redox reaction, and of course that's going to be 1 mark because of course it answers the second part of the second question. But why is that going to be the case? Well, I've got copper 2 plus, and that copper 2 plus is going to react with of course iodide ions, and what we end up forming is copper iodide, which of course is going to be copper 1 iodide. That's going to be our white solid, and then we also end up forming iodine solution as well. That's going to be our brown solution itself. This is a redox reaction that happens when we deal with thiosulfate iodine redox titrations. This is the first reaction. So yeah, there's our liberated iodine over there. Now, of course, if I were to balance this, I would end up putting a 4 over here, a 2 over here, 2 over there, and that balances on its own. Quite a hard one to balance because of course you need to have your charges balancing as well as the atoms. So yeah, there's the last 2 over there. Nice, easy. 1, 2, 3, 4, 5, 6, 7 marks in this question. So yeah, moving on then. If you were to look at the following task, a more trickier example, 6 mark style question. I want you to lay everything out in terms of layman's terms, just equations, just formula with the correct letters next to them as well. Feel free to pause the video and have a go at the following question. So yeah, looking at this question then, we're told here that we've got B and C, and they're going to be compounds of two different transition metal elements. A student carries out test tube reactions on aqueous solutions of B and C. The observations of the student's tests are shown below. If we were to break this down, we can see, of course, the first test is to test for transition metal ions, and then if there's any further changes, we know we can end up with specific ones. The next one is nitric acid to remove any carbonates. If it fizzes, we know, of course, we've got carbonate ions present as well. And then we've also got the barium nitrate test for sulfate ions, and then of course the silver nitrate test for our halide ions itself. Now just remember, when we deal with these compounds, we're going to have, of course, a positive charge and a negatively charged ion, and together they're going to make the actual salt itself as well. Now if we were to look at the question, it's actually asking us to analyze the results to identify B to H and construct ionic equations for the formations of products D to H. Now starting off, if we were to look at B and C and break down the question, we know so far already that, of course, we add ammonia dropwise, we end up with a green precipitate with D, and then we end up with a grey-green precipitate with E. But B itself is going to be iron 2+, because we end up with a green precipitate, because of course a grey-green precipitate is going to be chromium 3+, but we know for definite we've got chromium 3+, because that precipitate redissolved to give us a purple solution F, which we already know is a ligand substitution reaction. So yeah, this one is going to be chromium 3+. Now we found the positive ion in both cases. What about the negative ion? Well, in B, we end up with a white precipitate when we add, of course, barium nitrate. That means, of course, we've got sulfate ions present. If we were to look at C though, we end up with no change, but a white precipitate with, of course, our silver nitrate solution. So we know, of course, we must have in there some chloride ions itself. So we know, of course, B is going to have the following formula. That is going to be iron sulfate, which is just FeSO4. We know C is going to be, and then it's going to be our chromium, and then 3 lots of chloride to make it balance. There's the first 2 parts of this question done. Now, of course, the next thing is we've got to decide what D and E are going to be, as well as an equation to show how they're formed. Both of these are going to be precipitation reactions. Well, starting off, if I were to look at D, right, where we're actually reacting iron 2+ ions, and I'm going to include some state symbols here as well. Aqueous reacts with 2 lots of hydroxide, which is also aqueous. We end up with a precipitation reaction, which is what I prefer you to mention, but of course I don't have enough space. We end up with a solid over here, and that's going to be our green precipitate. If I were to look at E, how is that going to be formed? Well, again, we end up with a precipitation reaction where we end up with chromium 3+. Look at the charge, it's 3+. It's going to be aqueous. It will react with 3 lots of hydroxide ions because it has a charge of 3+. So we end up producing chromium, and then we end up with 3 lots of hydroxide, and then it's going to be a solid. So there's our next equation done there. So what about the next one? What about for F then? Well, we're going to end up with 6 lots of water ligands attached to our chromium 3+ this time. So I'm going to show the full thing. I'm not going to ignore them like I did in the previous examples. So I end up with 6 over here, and then of course my complex is going to have a 3+ charge. So yeah, I've got 6 lots of ammonia, and then don't forget your state symbols as well. And then I end up forming, and then it's going to be chromium, 6 lots of ammonia ligands on there as well, and then square brackets there, and that's going to be, of course, still 3+, because ammonia and water, they're both going to be neutral, aren't they? So yeah, we end up with that. That's also aqueous because they're both going to be solutions, both complexes. And then we end up with 6 lots of water, which of course we know is going to be a liquid. And there's our ligand substitution reaction there. So yeah, I've got here my 3 equations for D, E and F, and just to make sure I don't actually lose any marks, I'm just going to write out what D, E and F specifically are going to be, because we're asked for the equations for them, the ionic equations, but we also need to give the identities quite clearly as well. So D, we can see, of course, is going to be iron, and then it's going to be a hydroxide, which looks like this. Then we end up with, of course, E, which is going to be chromium, and then hydroxide, which ends up looking like this. For F, I end up with, of course, chromium, but it's going to be as a complex this time, so I need to be able to draw it out. Chromium, and then I'm going to end up with 6 lots of NH3 lots of ammonia, and then I end up with, of course, closing that bracket, and then I end up with 3 plus itself. So I've got D, E and F structures clearly drawn. What about, of course, the next one, right? What about if we were to look at G and H? Well, G is going to be quite straightforward, right? G is actually going to be, so I'll start over here on this line. G is actually going to be barium sulfate, but we need to be able to show that and how it's formed using equations. So G, in this case, we already know is going to be barium sulfate, so we're just taking barium 2 plus ions, state symbols again, because it's a precipitation reaction, it's going to be aqueous. I end up with barium 2 plus ions, I end up with sulfate 2 minus ions, they're both going to be aqueous, and we end up with barium, and then it's going to be sulfate itself, which is a solid. There's that one done. What about the next one where I'm dealing with H? Well, H, we already know it's going to be silver chloride because of the white precipitate. In terms of the equation though, we end up with silver ions, which of course they're going to be aqueous. I'm running out of space here. I end up with chloride ions, which again are going to be aqueous, and they end up making my silver chloride, which is going to be a solid itself. And so yeah, that's how you can get full marks in this qualitative analysis question, mixing year 1 qualitative analysis with year 2 itself.